Hello everyone, thanks for being here. My name is Siddhartha Reddy. I work as an architect in the website team at Flipkart. So this was Flipkart back in June 2007. Most of you, including me, might not have seen this, right? And this was Flipkart back in November 2007. And we started over there and we've evolved to what it is today, right? It was a big journey where we started from having just books on the website to what we have today. We started from possibly one visitor visiting a day to now millions of them visiting each day. And over this time, the Flipkart architecture has evolved quite a bit. Right? The architecture we have today is from somewhere around mid-2010. What I'm going to do today is I'm going to present to you how this architecture evolved over this time. Right? But instead of just giving you what the architecture was at various points in time, I thought I'll do this in a different way. I'll do this by presenting to you various issues we faced during this time, how we found out the root cause of that, and how we fixed those, and what learnings we are taking forward from there. Right? So I'm going to present this as the issues we faced, the root causes we found, RCA's root cause analysis, then the actions we took based on those that analysis, and then the learnings we take forward. Right? In fact, I'm going to be discussing just one issue which keeps cropping up again and again for any system which has to keep scaling up over time. Right? Website is slow, and other ways this issue comes up is, hey, website is down, or website is degraded, or website is throwing errors, and so on. So let's get started with the earliest days. Right? When it was a different architecture at that time, but the problems of scale were there. We started at nothing in 2007 and we're serving millions of requests by mid-2010. And we were just coping up. We were looking at the obvious, solving the most obvious problems that almost any website which goes through this cycle has to. Right? Let's look at the website is slow. Right? One of the first issues we faced, why the website was slow, was due to the database queries that we were doing. So we used to and still use MySQL as a primary data store. And in this, we started facing lots of issues with slow MySQL queries. And when we started digging in, what is the reason behind this? It was just a matter of too many queries. We were growing at a pace. We were growing so fast that our systems, our database was just not able to take the load, additional load that this growth was imposing. We were almost doubling the traffic every 3 months or so. And it was just a matter of capacity, right? And how do we fix that? The most obvious way is to add beefier servers. You have a server with 8 GB memory, you get a server with 16 GB memory, right? Well, that's something that you can keep doing for a while, but there's always going to be a limit to that. At this time, we started taking a deeper look at how we structure our databases, how we structure our systems, how we architect them. And we said, okay, we need to start doing more realistic. We need to be having an architecture which works for the kind of scale that we are looking at and the kind of growth that we are looking at. So the straightforward approach was to separate out the databases into a master database and a slave database. All the writes go to the master and the reads go to the slave. Right? What this does is very simple. It allows us to scale by scaling out rather than scaling up. We don't need beefier servers, we just need more number of servers and more number of commodity servers. This also does something very important. Writes in a system like us, in an e-commerce system, are actually very, very important. We don't want to be in a situation where we accept a payment for an order and then don't have a record of it, right? So writes are far more important. And by separating the reads out into a separate system, what we are able to do is that we're able to guarantee that the writes, which are, by the way, far fewer in number compared to the reads, are always going to a system which is able to handle them. Right? So the learning we could take away from this is that we could scale out databases by at least the database reads by adding more servers and distributing load among them. I just showed that there is one MySQL slave we added. We could add 3, we could add 4, we could keep adding any number of MySQL slaves and distribute our read load among them. Right? We could just scale out like that. And separating and isolating the reads from the writes allows us to make sure that the usually more critical writes are always given this importance that they need. So moving on from here, we solved most of the issue with MySQL, right? So with slow queries and all. But website was slow again. I mean, it's not like it was always slow. So issue keeps cropping up once in a while saying, hey, website is still slow, intermittently throws errors, whatnot, right? And we started digging in. MySQL slow queries were slow again. Right? This time the reads were slow on our read databases. What is happening? Same story. It's repeating. We could simply go and add one more server and say, hey, we distribute, but we said, okay, let's take a deeper look at why it is growing at such an alarming pace, a pace that we didn't expect it to grow. Turns out, it was not just the users who were hitting us. It was not just the users who were scaling. It was us. We were actually starting to look at the data we have very deeply. We were looking at a lot of analytics. We were trying to understand the user's behavior. And to do all this, we were trying to do a lot of queries on our system. And all these queries were also taking a toll on our MySQL systems. And how do we fix this? Well, the solution was, we have this one MySQL slave or a set of MySQL slaves which are being shared by both website reads and writes, reads as well as analytical and reporting reads, right? We split it. We say, hey, we have a dedicated MySQL instance which is for analytical or reporting purposes. And we could have one or we could have a set of them, right? We don't need to have one. And not only does this allow us to make sure that the website reads are isolated and we never slow down the website due to some reporting that we are running, but this also allows us to optimize this single MySQL slave for purposes for which we are using it for, analytical and reporting purposes. We could use stuff like, use MyISAM engine for MySQL, which is optimized for reads instead of using InnoDB, which is optimized for low contention writes, right? And we could add additional indexes on this MySQL slave, which are specifically for reporting. We wouldn't want to add that on the production database because it would slow down our writes in general, right? So the learning we take away from that is a very important one, at learning that we want to and sometimes have failed to apply, and it has always bitten us. That is, isolate the reads, isolate the databases that serve production traffic from databases that serve the backend jobs. And it's not just about databases, it's any systems that can potentially serve the production live traffic, as well as some background jobs we have and backend jobs we have. We need to isolate them. We need to make sure that anything we are doing for our own purposes does not impact our users who are browsing the website or placing an order on the website. Right? So let's move on to the newer architecture. We move to a newer architecture. We have a larger amount of scale now. We have started moving to a service-oriented architecture by this time. And we started facing newer kind of issues. We were past the issues of, hey, MySQL is slow, or mostly past it, right? But website is still slow. Right? Website continues to be slow. And we started digging in. Right? But before we dig in and say, hey, this is why the website is slow, we need to understand how to do that digging in, right? So we started adding lots of instrumentation. So our code was just filled with snippets like this, like where we go and say, hey, we're going to start this activity, and this is when we have ended this activity. And this piece of code that goes and records information in various kinds of systems saying, hey, this part of the request handling took this much time, this much CPU, this much user CPU, this much system CPU, and so on and so forth. Right? It took this much memory. This allowed us to see and observe our system and each part of that system. And I'll present a few different RCAs, or root causes that we came up with, which have a common theme. I'll come to the common theme soon, right? So I just said we started instrumenting a lot, and all those went into some log files. But the problem is, all this logging was taking a toll on the system itself. And talk about the uncertainty principle, right? So you start observing the system, and just the fact that you are observing the system is causing it to get slower, right? So this comes down to the PHP's process model. So we use PHP for our website front end. Now, the way PHP works is each request is run by an individual process of its own, an individual Linux process, right? And all these different processes we're trying to log and log to the log file. Now, there is one single file to which all of these processes are trying to log. What happens? Only one file can at any time, only one process at any time can actually have write access to that file. It can be writing to that file. So the other processes just queue up behind it. So as we start handling a lot of concurrency, a lot of requests in a single server, all these processes are just competing with each other just so that they could write to the file. Right? Now, unfortunately, PHP does not give us a lot of levers here to be able to work around this problem. How did we work around this problem? Before I come to that, let me give a couple of other instances of issues, other kinds of issues we started facing. I mentioned we started becoming a very service-oriented architecture, right? That is, most of our systems were becoming services that we started accessing. So website would go and start making lots of connections to these services in order to serve a single request. So we get a request to serve, let's say, a search page. We go and make a request to our search service, get the results. The search service just returns, say, the IDs of the products that need to be shown. We then go to our catalog management system, or CMS, and get the product details from there. We then go to our user rating review system to get the ratings for those products, and so on and so forth. We just have to hit all of these different systems to gather the basic data that we want to be able to serve. Right? Now, this takes a toll. For every request, we have to make, say, 4, 5, 10 connections, 10 different connections to 10 different services, get the response from them, and serve that. Now, this is expensive for a number of reasons. One, very important thing is that we have to make these connections to these services on every request. The reason for it is, again, PHP's process model. As I mentioned, each request is served by a different process, right? Now, that means that we cannot have a connection ready before the request starts. So we have to make that connection while the request processing is happening. We cannot have what is called a connection pool. PHP just does not allow us to do that kind of thing. Right? In addition, PHP's multi-threading is non-existing. And there is no multi-threading in PHP. That means all these service requests have to go in a serial order. Right? That's sad. So we could be making many of these requests in parallel. As an example, let's say you search under all categories under Flipkart, right? So we have to hit probably 10 or 15 different indexes, right? 10 or 15 different search indexes, and then pull all of that data and merge those data together. This could very easily be parallelized. There is no reason for that to be happening serially, but PHP forces us to do it in a serial order. One more very interesting instance we found was that our configurability was hitting us. So we had, by this time, built a website which was extremely configurable, which is true even today. You could change large parts of Flipkart website without ever deploying any code. You could just go to a console, change a little bit of things there, which goes and changes stuff in the database, and boom, the website has changed. You could change the products on the homepage. You could change the complete homepage. I mean, what you see on the homepage, the modules you see, the products you see in them, everything could be changed just by changing some stuff in the database. Now, what does that mean? That means that for every request, we have to fetch all this config before we serve it, right? So you get to the homepage, we have to go and fetch all the config that is required to be able to serve the homepage. This is a lot of database queries that need to be, and it suffers from all the problems that I just described. Since we don't have connection pools, each of these config calls is a fresh connection, or at least there is one connection for a request that we need to make to the database. Also, this is the kind of config which you would ideally want to cache within the system, right? This doesn't change as often. Maybe it changes every hour, maybe it changes every few minutes, but not more than that. And we would be serving hundreds of requests every second, and for each of those requests, we will be going to the database and fetching that data. Makes very little sense. But again, because PHP does not have a shared state between processes, we're not able to do much about that, right? So just recapping, logging was a problem that we saw. SOA, or service-oriented architecture, because of going there, we faced problems due to not having connection pools, not being able to parallelize requests, and configurability. And all of these problems really point back to how PHP's process model is, which is not good news for us because we were really invested in PHP. We had developed a lot of code in PHP, and it's not that we could just move away from it. And PHP anyways was good for us in many other ways. It offered us agility and things that not every language would be able to, and our developers were well versed with PHP by this time, right? So how do we fix this? So we came up with what we believe was an innovative solution at that time. we like to call it FKW3 agent, right? This FK is Flipkart, W3 is website agent. It's agent, it's a Java middleware that sits on every one of our web servers. Now, what PHP is not good at, we let this take over that and do that, right? So it's a very simple piece of software, runs as a daemon on every one of our web servers. PHP communicates to this daemon through a very local socket, very fast connection. It's the connection and the exchange between PHP and this Java process is less than a millisecond. We can't even measure it on most systems. And then we can write pluggable handlers as part of this agent, which can do all these things that PHP is poor at. I'll give the examples of what the handlers, how we solve the problems that I just mentioned through agent, right? So let's look at the logging handler, right? Earlier, what we used to do is we used to have all these processes to write directly to the log file. Now what we did is instead, all these processes hand over the log that they want to write over to the Java process. It's a very quick, sub-millisecond, just hand it over. Now this Java process takes these logs, serializes them, and writes them to the disk after buffering it. Right? It frees the PHP process to complete the request without making it stop for write and flush the log to the disk. Right? By the way, if someone wants to interrupt me and ask any questions in this, please feel free to do that. Right? Don't have to wait till the end of the presentation. Right? Let's look at yeah. Sure. Yes. So that's a good point actually. So I had it in my slides, but I didn't mention that while going through it. So there are we divide the reads in the system to critical reads and non-critical reads. Right? Reads that happen immediately after a write are critical reads that still need to go to the master DB. So you, as an example, you make a payment, you go through a checkout process, and you say, hey, confirm this order. We redirect you to an order confirmation page, a page which says, hey, your order is confirmed. Now the checkout would write that, and then we would immediately redirect the user, and that page would say, hey, your order is confirmed. That page needs to reload the same order details from the database. Now, if there is a replication lag, if the slave does not receive this write, by the time we reach that order page, that's a bad thing, because that order will not be found. So that's an example of a critical read, a read that is reading data which is happening immediately after a write. Now we have, in our MVC framework, we have made it possible in our data layer to specify which are critical reads and which are not. So the critical reads always go to the master. They still go to the master. The non-critical ones, which are not reading data that was possibly just written, they go to the slave. So each controller is able to specify for every kind of query that we are doing, whether it's a critical or a non-critical read. We have built in that support into our framework to make it possible. Does that answer your question? Thank you. All right, so let's see how we've solved the problem of making too many connections and making too many requests to different services, right? So this is what we used to do. We used to have a request, connect to a service, send a request, get the response, continue, and so on. What we moved to instead is don't connect to the service directly. Connect to call FKW3 agent and have a specific handler there for that service. Let's take the example of the search service, right? So there is a search task handler, within our agent. So we make a call to that. That keeps connection pools, that keeps ready connections with each of the services that it needs, each of the hosts that it needs to contact. And it reuses those connections, and it can also parallelize these calls. In fact, we do exactly that in our search service, right? When you search under all categories, we fire off a fork join kind of, it's a fork join kind of model where we fire off all these 15 queries in parallel, wait for all of them to return with appropriate timeouts everywhere, and whatever returns, we just give it back to PHP. PHP is blocking on this until then. Database every 500 milliseconds. So within a second of making any change on our console, we can actually see it on the website. That's a lot of power. Especially that's a lot of power that we are able to give to our business folks who are making these changes. Yeah?
How different is this from using a generic memcache? Like, is it doing something very specific for configuration, or it's a generic memcache that you can do?
Okay, the question is how different is this from using a generic memcache? There are a small amount of differences. One, this is not a lot of data. This is possibly a few tens of thousands of entries, right? Which are very easily cacheable in memory within a single system. Now the fact is, this is cached within the same machine, same server that the PHP process is running. So we actually don't make any network call. It's a local fetch. It's an in-memory transfer effectively, right? Linux kernel is very, very well optimized for a call to local host. It doesn't go through the full network stack. It doesn't have to go to the driver and so on, right? So that's one optimization. The other is the way this actually works. Most of our PHP code does not need to know that it has to make this special call. The way they do is we have a config class, right, which has a lot of variables, which have some default values. What we do is in the init process, during our frameworks init, for that request, all the config is fetched from agent, and these variables are overridden. So the rest of our PHP code never realizes that these variables are coming from our agent or anything, right? They just behave and use these variables, these config, as if it's just a config in another PHP file out there, right? So it's a much simplified process model, much simplified programming model for our processes, right? So, sure.
I just wanted to know, would you be turning this agent into a single point of failure, or how do you handle failures with this agent? Because I think there is a lot of reliability on this doing a lot of things for you, right? So how do you basically go about handling that?
Yes. So it's not a single point of failure because there's not one instance of this. There is an instance of agent on each of our web servers. So we have 10 web servers, let's say. Each web server will host one instance of agent, right? Yeah.
That you introduce in a particular version, how would you go about handling that?
So that's a standard way we handle. So the issue could be, we could introduce that same kind of issue in our PHP code as well, right? It's the same way that we try to handle everything else. We have a very good QA process which makes sure that automated QA, which makes sure that bad code doesn't go. We have unit tests, we have testing. Before anything goes live, we have all kinds of testing and barriers in between. Then we are starting to do what we call ring deployment, wherein we deploy any new code to say 10% of the users only. And then we start observing all kinds of metrics. We see performance metrics, other system metrics, business metrics, and make sure that nothing is changing drastically due to this deployment. Right? If anything, we roll it back. Otherwise, it gets rolled out.
There's no failback mechanism or anything that you build into this?
Failback in what way?
If something is not working, for example, there are 3 or 4 pieces that you said, right, which is actually dependent on this particular agent.
Yes.
So let's assume 2 or 3 is working, but one piece is not working. So is there an alternate fallback mechanism or something that you...
So it depends on one thing to the other, right? So logging, let's say, is not working, right? It's okay. It's not a life and death situation. But let's say the search handler is not working, right? That's a problem. We earlier used to have a system wherein if there is something wrong with agent, we had PHP code as a fallback, which could do the search by directly hitting in the serial order. It would be slow, but it would at least work. But over time, we have started relying more and more on this agent. It has been a very stable system for us. It's been around for more than 2 years now, almost 2 years now, actually. And we have come to rely far more on it now. So we are able to trust the system, and it goes to more stringent mechanisms for testing, right? So it's not a system that we may often change too often.
Have you tried something else before coming up with this agent?
Sorry?
Have you tried something else before making this agent?
Something else in
like APC for config variables or curl multi for parallel request, something like that.
Yes, in fact, we do still use APC for a bunch of config. The problem there is that, for example, if we store this config in APC, in fact, after fetching this from agent, the W3 agent, we actually cache it in APC as well, so that we don't even have to go to agent on every request. But the problem with storing it in APC is we need to figure out how to invalidate. APC is a cache, and as soon as we start using a cache, we need to try to answer a bunch of questions about how we ensure consistency of data. What happens when config changes? How do we get the latest config in? Right? That is what agent is able to do, because it has a background thread which keeps polling and fetching the latest things. So what we do is APC cache, we cache it with a TTL of 1 minute. So after a minute, it's not, those keys are not present in the APC. We go and fetch it from the agent. So once every minute, we actually go to the agent. But agent is refreshing it often enough that we achieve both the things. Right? There are actually other systems quite similar to agent. So there is an open source system called Gearman. We didn't know about Gearman at that time because it was just coming up at that time. Gearman, which solves the same problems that agent does. Right? So simple learnings, PHP is great for front-end and templating, what we really started loving it for, what we started using it for, right? It gives us a lot of agility in those ways, right? It's not a compile language, interpret it, make a change, refresh your browser, and it's all there, right? But it has a very limiting process model, which limits how we are able to build high-performance websites with it. Java, on the other hand, gives us stability and performance where we need it. So we continue to use both for what they are good at.
Excuse me?
Yep.
So you mentioned the advantages of using that agent, Java agent. What was the, what problems did you see, or do you see any disadvantages of using that kind of system? You only mentioned the advantages there. That okay, it can, perform parallel or thread-based operations. Like, what were the drawbacks of using such a system?
So the biggest drawback is that.
Or what problems did you face?
Sure. So the biggest drawback of using this system is that we have one more system, right? So one more system, one more point of failure, one more thing that needs to be monitored, one more thing that needs to be kept up, one more thing that needs to be tuned, and whatnot. But it was a trade-off. This gave us the stability and performance that we needed, which we were not able to extract from PHP, or which we at least had to go through too many hoops. I mean, there were other ways to solve this. We could have written C hooks into PHP, right? We could actually write code in C and hook it into PHP, integrate it with PHP. But that would all be far more cumbersome, and it would be very error-prone, because writing into the PHP stuff into the PHP interpreter and all would be far more error-prone and would not give us as much flexibility in terms of, so now that we have this one thing called agent, right, we have, I think, close to 20 plus handlers within that, doing various different kinds of things. We're able to have this simple system, and all these people who are writing handlers, right, the handler mechanism is very simple. It has a function that receives a bunch of arguments, does whatever it does, and returns, right? It's as simple as that. The model in which we write these helpers has become far simpler than, say, if we had gone the route of writing this code in C and plugging it into PHP. Right? So, horses for courses. Right? All right, let me give another. Okay, again, the issue is the same. Website is slow, and what's wrong this time? Thanks to our instrumentation, we knew that we were just taking far too much time in our PHP processes. Now, and when I say time, I don't just mean time waiting for I/O, right? This was actual CPU time that we were taking up by our PHP processes, right? And when we dug in a little deeper, there were two very big bottlenecks that we were seeing, right? We have this product information object, right? Every product's information that had started to grow very huge because we were having very granular information about product. Right? We were investing a lot in our catalog system to be able to get very granular information about every product. But that also meant that the size of our product objects just started bloating up. And just mere deserialization of these objects, once we fetched them from our catalog management system, was taking up far too much CPU. So we used thrift as the serialization format, but it was just taking far too much CPU. Also, our website was growing richer, right? Richer and richer. So we started to have very rich page construction, and all this construction of the HTML, it's a very heavy string operation. It's very CPU bound, and it was taking up far too much CPU. There were instances of bad code, badly written code, which we went and fixed, but these were fundamental problems which we couldn't solve in any simple way. And the solution for this was caching. Right? We started caching a lot of things. Like what? Like we started caching fully constructed pages. So the home page, for example, probably changes only once every few minutes. Why keep reconstruct it on every request to the home page? We could just cache all of it, right? But we only do this for the highly trafficked pages like homepage or say books homepage and stuff like that, not for every product page out there. So we have close to 20 million products. That means 20 million unique pages for each of those products and a multitude of other pages. We cannot go and cache all of those. And there will be little value in caching all of those as well because they don't get hit as much. On the other hand, our homepage gets hit hundreds of thousands of times in a very short span of time. And caching it yields a lot of benefit. Right? We also started caching the product object, but not just caching it. We were caching it to save on deserialization time. So what we decided to do was we decided to cache the PHP serialized object. So we would fetch the object, deserialize the thrift, serialize it using PHP serialization, and store that in the cache. Now, PHP's native deserialization is faster, much faster than thrift deserialization. This is something that can be expected, right? The native object deserialization is going to be faster. So this was a huge cache, like close to 20 million objects. In fact, it actually had close to 60 million objects because every object had to be stored against 3 different keys, due to some internal details, right? So we used external cache, memcache in this case, for this. So we had memcaches going up to 100 GB. Right? But adding caching is adding complexity. Caching can lead to inconsistencies. Caching starts leading to lots of problems. Let's take an example, right? So we said we'll cache fully constructed homepage. But what are the problems with that? Well, the simplest problem is that there are parts of the homepage, even homepage, which still need to be dynamic. I mean, if you're logged in, you want to see that you're logged in the header. You want to see your name there. You want to see the logout button, not a login button there, right? So these parts of the page still need to be dynamic. We actually went ahead and solved this problem. So we built the support for page level caching into our MVC framework, and each view could specify whether it's a dynamic view or a static view, and only the static views would get cached. The dynamic views would get rebuilt on every request. But there was another problem that we actually couldn't solve. At Flipkart, we like to do a lot of testing, A/B testing or bucket testing, right? Whenever a feature is going out, we like to put it out to say 10% of the users, 20%, 50% of the users, observe how this feature is impacting various metrics compared to what we had earlier. Now, this caching made it impossible to do A/B testing on these critical pages, right? So if we have to do, it's not impossible. We have done this, but it was very, very cumbersome. So cumbersome that, which is as opposed to the really simple way that you could do A/B testing in other parts of the website, which were not cached. I mean, it was just write an if-else or write an additional file and you're done. It was as simple as that, but this caching complicated that quite a bit. This is a problem that we have not solved in a very satisfactory manner even today, right? So let's look at the other thing, right? Caching PHP serialized product objects. Now, let's look at a scenario when, what happens if we didn't use cache, right? So get product info, pass it a bunch of IDs, it would return the product. So that's a method. It would just fetch this from CMS. CMS is a catalog management system, the service which hosts all our catalog data, our product information, right? It's a simple fetch, right? The problem with that is though that the thrift deserialization we have to do after that is very CPU heavy. Now let's look at the case when we do use caching, and there is a cache hit. That is, the object can be found in the cache. So it's a get product info and fetch from cache. The reason the second one is better for us than the first one is not because CMS is slow, because CMS is very performant. The reason is that the deserialization of the CMS object is very expensive. So the second one avoids that and makes it better. But let's look at a case when we use caching, but there's a cache miss. So we call the get product info object. It goes and tries to fetch this object from the cache. It doesn't find the object. So now it goes and tries to fetch it from CMS. It does the thrift deserialization. Then it does the PHP serialization and sets it back in the cache, right? So if you look at the first row there and the third row, the third one, when using a cache and no cache hit, we are much worse off than not using the cache at all, right? So in this case, we are doing 2 extra network calls and 1 extra serialization compared to what we did without caching. So that means we added cache, but now we have bought ourselves this nice problem that if we have a cache miss, we are actually worse off than not having. That means, let's say our cache goes down, all of a sudden all our calls are twice as slow when compared to when we were not using the caching, right? So how do we solve this problem? Right? It's not a straightforward problem to solve. So what we did is we said, hey, the TTL of the objects we set in this memcache is infinity. That is, these objects never expire. Right? We do not invalidate the objects that we set in our cache. But that begs the question, what happens when the product information gets updated? And it gets updated a lot. Right? We have close to, I think, 100 to 150 updates every second. Right? That's the rate at which they get updated. What do we do? So we proactively go and repopulate the products in the cache which have changed. So for the website keeps getting the products always from the cache, and everything is always in the cache. But there is a background job which goes and repopulates these products whenever they change. How do we do that? So our CMS system pushes out a notification whenever there is a change in a product. It just publishes a notification saying, hey, this product has changed. Right? We have an in-house platform called the notification server, which is able to take such notifications and deliver them to specific endpoints. We have a HTTP endpoint which it delivers to, which picks up these product IDs, makes the CMS call, and then publishes it to the cache. Right? And we also switched to using persistent and distributed caches, because, like I mentioned, a cache miss in this scenario is actually worse off than having a cache, no caching at all. So if we are just in memcache, and memcache is an in-memory cache, what happens if the system goes down? Right, boom, we lost everything. So we did have a sharded cache. It's not like we had one instance of memcache with 100 GB of data. We distributed it across many instances, and we had a nice little library which would handle this sharding and rebalancing and so on. But still, if a machine goes down, if memcache goes down, that means we lose all those products. And any hit for all those products now starts becoming much more expensive than no cache at all. So we switched to using a persistent distributed cache. So we started using Membase first, and then we recently actually moved over to using Couchbase. And this is working out very well for us. So it's a distributed, there is replication, so it's a cache farm that we have built, which we use now. Right? So, yeah.
CMS pushed the notification. How was the failure mechanism handled there, in the sense the notification might not have been delivered onto one of the agents probably? How did you find out whether it is delivered or not, because it could be stale?
Sure. So the notification is not actually delivered to the agent. It's delivered to one endpoint which is dedicated for it's delivered to the PHP process. We need to store PHP serialized object, right? It's a HTTP endpoint. Now, notification service actually handles this very gracefully. It has mechanisms for understanding when a service has not accepted and acted on that notification. It can retry. So we can set up how many retries to do and so on. And if something keeps failing, it puts it in a sideline queue. We can go and raises an alarm, so we can go and see, hey, these things have failed.
Okay.
How do you handle race conditions in that?
Race conditions of what kind, sorry?
For example, like I'm assuming that there are multiple writes happening. Okay. Multiple people are actually updating the same product. And the notifications are actually going to your notification server, right? And let's say the request number 2 has actually failed. Request number 3 comes in, which requires information from request number 2. So how do you handle that?
So the thing is, the notification server doesn't actually push the modified object. It just says, hey, this object modified. This is the identifier for this object. Now, the system which receives this notification actually goes back to CMS, asks it for the latest version of that object, gets that, serializes that, and then puts it in the cache. Right? So that avoids the race condition. Even if we miss one of the notifications in between for that product, right, and we get the next notification, the latest notification is, latest version of the product is what goes into the cache. Latest version as published by CMS is what goes into the cache. So caching is a very powerful tool for optimization, right? But caching adds a lot of complexity, and caching is best when it is close to the data source. In this case, CMS is the data source that we are talking about. Caching is a very, if it is close to that, the complications are reduced. But as we move the cache further away from the data source, the more complications we add. So in this case, caching, because it's with the website instead of being with the CMS, it has added so many complications, right? We have to think very deeply about the TTL and validation. Those remain, cache invalidation remains one of the hardest problems in computer science, as someone said, right? There's only 2 hard problems in computer science, naming things and cache invalidation. Well, all right. So, in general, the principle we like to follow is that caching is a way to go from acceptable performance to awesome performance. So we are already at a levels of acceptable performance, and we just want to take it to the extreme to make it really awesome. That's what we want to use it for, not to just reach acceptable performance. That's not a very good system where we rely on caching just to get to a acceptable performance, right? So we started growing up now and started facing newer kinds of issues. Of course, the issue remains the same. Website is slow. This is a very interesting one, actually. So let's say search service is slow, or review service is slow, or recommendation service is slow. But the entire website is slow because of that. I mean, if search service is slow, only search pages should be slow. Why is the homepage slow? Right? I mean, that's perplexing. Well, the reason was that the slow service was blocking out the resources that are needed for the other processes. Right? Let me explain that with some math. Right? Let's say, and these are simplifying assumptions, let's say that the mean response time of our pages is 100 milliseconds. And these are numbers taken for convenience. Right? And we are working on an 8-core server. Right? And for the sake of this argument, let's say all our requests are purely CPU bound, which is not true in most web systems. Right? We are IO bound. We make a lot of service calls to IOs. But let's make that simplifying assumption to demonstrate something here. Right? So the throughput that we are looking at is about 80 requests per second. That means each CPU core is able to do 10 requests in a second, because 100 milliseconds into 10, 1 second. Right? Now, let's say the 95th percentile of system is 1000 milliseconds. Now, what does that mean? That means 5% of our requests take 1000 milliseconds or more. Let's simplify that. Say 5% of our requests take exactly 1000 milliseconds. Now, let's say 4 such requests arrive at a server in a second. Right? That means our throughput has reduced down to 44 requests per second. Why? These 4 requests are occupying 4 cores, and the remaining 4 cores can do 10 each, so 40 plus 4, 44. Now, what happens if 8 such requests arrive at a server at any given moment? Right? Boom. That means our throughput for this server has gone down to 8 requests per second. And what if this persists for a while? If this persists for 10 seconds? We have created a huge backlog of requests on our servers, and things have started going bad, and they're never going to come back. We've increased the load average on our server beyond 8, 10, and it's just going to climb up, and that system will have to be rebooted. This has happened to us, actually. Right? So how do we fix this? I mean, there is no magic solution for that. So what we do is we say we have very aggressive timeouts for all service calls. Right? No service should be blocking out resources that are needed for other services. Right? Also, very, very aggressive timeouts for non-critical services. Let's say we want to show recommendations on a search page or a product page. That's not critical information. I mean, even if we don't show the recommendation, the page serves its purpose. Right? But there are pages where recommendations is critical, like the My Recommendations page. Right? There we cannot be doing that, but it's a call that needs to be taken. Even better, what we do with our recommendations is we don't even load them synchronously. We let the page go out, and we do a AJAX call back from the client to load the recommendations. That means we won't make the user wait even a single millisecond, because we want to serve recommendations to them. They are there to look at that product and that product information. We'll serve that as soon as we can, and then we'll go and fetch the recommendations. Right? Cool. I'll actually wrap this up here. So, any questions?
Event-driven programming server, let's say Node.js for that, and because it can actually process requests on demand.
Sure.
And it's easier, plus it has got lots of NPM available now. It's pretty much stable. So are you guys actually looking into that direction?
So yes, and it's a little complicated for us though, because of PHP again. So what we do is we do this inside our agent. So as an example, when I said search under all categories goes to 15 cores, right? What if 3 of them are slow? The remaining 12 have returned fast. So we don't wait for those 3. So we go and have timeouts, and we make sure that whatever data has come, we'll just go and serve that. So we do that, but as part of by moving that code to our agent, where it is possible to do non-blocking work. PHP does not provide any way to do that well.
And another last point is actually, instead of creating this FK agent, whatever you have created in Java, wouldn't it be better to write a C modules or as an extension specifically for PHP? And because you use PHP, I use PHP, and make service calls with that, because PHP is going to be very cheaper in that point. Memory usage would be low. There is no additional CPU usage that you'll see. Wouldn't it be better that you create something in PHP itself?
Well, yes and no. It would be better in terms of the raw performance if you go down to it. But at the same time, it would add a lot more complexity to our programming model, right? So each time we have to make a service call like that, we go and write a C module. Right? That takes a lot of work, it takes a lot of testing. Instead, we have created a system within which you can easily plug handlers. So like I said, we have over 20 handlers within this single agent system now. So we have made it really easy for guys to go and build high performance components within our systems, rather than go and build PHP modules, which add a lot of complication in terms of testing, in terms of making sure they don't run amok and destroy the entire process, in terms of deployments and a lot of other things. Right? So the way it works is we have, let's say, 10 web servers, and we have a load balancer where the requests come, and it distributes these requests among all the servers. So earlier, what we used to do is we had an equal random distribution or a round-robin distribution. Each request goes to one of these servers. Now, what we have started moving towards is sticky sessions. So the load balancer knows that, hey, if you are this user, then you should be sent to this particular server. It's not one server, this particular cluster of servers, let's say. Now, as your request comes in, it always goes to that cluster. Now, what we could do is we could say, hey, we'll deploy our latest code only to this one cluster. So only the 10% of the users who are reaching that cluster get that. Then from those systems, we start observing all kinds of metrics, system performance, general metrics around each service performance, page performance, business metrics, like how many orders are getting placed. Is there a sudden drop in the number of orders or anything? And based on that, take a call whether to proceed with deploying to everything or not.
So even if I come after a couple of weeks, I'll still be sticking to the same machine.
That's actually configurable through our system. So our load balancer, we typically have, depending on our what testing duration we want for that deployment, we can change it actually. So it can start from a few minutes to a few hours usually. It can also go to days, but that adds a lot of load on the load balancer itself.
So it's possible that I see a new feature someday, but again go back to seeing old features some other day.
No, so we never keep a feature to 10% of the users for more than a small amount of time. I mean, if we either know that it's not impacting anything and we roll it out to everyone, or we know it's impacting something, so we roll it back.
Thank you.
All right. Thank you very much.